Hey everyone, Fraser here. So as you probably know, there's been an announcement in physics, the muon G-2 experiment, and it's fairly technical, a lot of insider information in the particle physics community, and so I decided this is the perfect time to reach out to an expert, bring in a bigger brain, and in this case, I called on my good friend, Dr. Paul Sutter. You might know him as Ask a Spaceman, but actually he is also quite knowledgeable as a particle physicist, and so he was able to explain the G-2 experiment to me and help us sort of put the whole discovery into context. So I hope this helps you understand what has been discovered and what this means for the field of physics. All right, here's the interview. All right. Okay, we're live.
Yay.
Yay, we did it. That was
We did it.
so much technology.
So many buttons.
so many buttons that I had to press. Hey, Paul, how's it going?
Pretty awesomely. How about you, Fraser?
It's going really well. We haven't actually talked we've talked on the interwebs, but we haven't actually talked in person for a while. So
No, like mano a mano.
Yeah.
We have not.
Yeah.
It's been too long. How's the COVID going?
It's a disaster in Canada. It's an absolute nightmare. Yeah, no, we are, they're vaccinating 65-year-olds.
Oh, so you're eligible.
I'm just eligible. Yeah. No, my dad just got his first vaccination. He's going to come back and get his next one. But we're experiencing probably the worst outbreak. Like if every other country you see sort of they're starting to tail down now.
Right,
as the vaccine. No, we're as high as we've ever been and higher. No, we've
just like the situation in a lot of Europe too.
Yeah, exactly. Yeah, Ontario's has gone for its third complete lockdown. Yeah, it's super bad. I've talked about this that we, a lot of the time we feel like we're a version of America, but then every now and then you realize that we are. There's a border. It separates us. We're not like you, and we are the customer. And so we're sort of like patiently watching as you guys are all done vaccinating each other.
Right.
And then maybe you'll ship some over the border and we can buy some.
Have anyone set up like very cruel vaccination clinics just on our side of the border so you can watch like 16-year-olds getting shots in their arms?
Yeah, exactly. We would if we could leave the house, but we're not allowed to. So, there would be no audience for that. But
I got my shot on Saturday, my first shot of Pfizer.
Your first shot. Okay. All right. How are the side effects?
I felt kind of crappy all day, but that's, like a normal Saturday for me.
Yeah,
so
exactly.
It wasn't much difference.
That's just like allergies, I think. I blame everything on allergies at this point.
Fair.
Cool. Well, so for people who don't know who you are, who are you?
I am Dr. Paul Sutter. I'm an astrophysicist at the Institute for Advanced Computational Science at Stony Brook University and the Flatiron Institute in New York City. And I host TV shows, I write books, I do podcasts, and whenever Fraser tells me to show up, I show up.
Right. And vice versa. I'm here. I'm here for you as well. I think the thing that most people don't know is that you are as much particle physicist as you are astrophysicist cosmologist, aren't you?
The best thing about astrophysics and cosmology is it encompasses so many cool areas of physics. And so in order to understand some of the highest energy processes happening in the universe, you have to understand high energy processes. And so that is high energy physics. So there's so much intersection between the worlds of particle physics and cosmology.
And so I wanted to bring you on to help explain the muon G-2 experiment that's happened. Have you sort of prepared? Have you done this several times so far? How many of these have you done so far?
No, this is my first.
Oh, is this your first? Okay.
I was on vacation last week, actually.
Right.
And so like all the news is happening and it's like, I am just on vacation. I need a vacation.
Yeah.
I need to just chill out and stare at a wall for a week and not talk about science. But now I'm ready to go.
All right. So I'm going to help you workshop your muon G-2 experiment explainer.
My elevator pitch.
Yeah, exactly. Yeah. You got 15 seconds. Go. No. All right. So then I guess Where would you normally start with this? I'm interested to see where.
Let's start with the muon.
Okay.
Like who cared? How all of a sudden we care about the muon.
Yeah. Well, there's a lot of particles. There's a lot of particles out there. Yeah.
There's a lot of particles out there. It's a whole messy zoo out there. It's crazy. Why we care about the muon, or first, what the muon is, it's exactly like an electron, except heavier. That's it.
It's heavier.
It's heavier. It's heavier than an electron.
But is it an electron? Like, could I power my computer with muons?
Yeah, but good luck with that. Like, seriously, like a muon, it has the same electric charge, the same spin, the same. It's all the same, except it's heavier. And so, because it's heavier, you could, in principle, build a computer out of it. But good luck, because it decays very quickly.
These are just details. My point is, I could jam muons through a wire, a beefy wire, and compute through AND gates and power my home of the future with the electric charge carried by muons. It is
with the muon. So there you go. Why don't you sell that idea to Elon Musk and you're good to go.
All right. So
but the downside is, because they are so heavy, they last like 2 microseconds.
This is not my problem. I don't need to. Yeah.
It's an engineering problem.
Well, how long does an electron last?
Like forever.
Oh, okay. Yeah.
Yeah. Like literally forever.
So electrons are like much better versions of muons. They've had all the bugs worked out.
I mean, hey, that's a matter of perspective. We're not going to mass shame any particles here.
Yeah.
Just because it has heavier mass than an electron is just as worthy.
Okay.
Just as, it's just fine.
Okay.
We love muons.
Right. How do we make them?
Muons come about so you can make electrons through all sorts of complicated nuclear interactions. Like, you can slam stuff together and then electrons pop out. You can just slam other different kinds of things together and make a bunch of muons pop out. And so we have muons coming out of our jets in our particle colliders. When high energy cosmic rays strike the atmosphere, they create showers of muons. It's one of the many things that come out in these complex particle interactions.
Okay, so I think we've set, I guess we've put a bookmark on what the muon is.
Yep.
And that it's different from the electron and so on. Why is this the particle that the physicists have been experimenting with?
Because we're very interested in a particular property of electrons and muons. And there's even an even heavier sibling called the tau, and we're not going to talk about the tau right now. But we're interested in a particular property called the magnetic moment. And this is, in the physics world, this is labeled as G. I have no idea why. I guess we ran out of all the other letters. So we just call it G.
Strange quarks. Like,
why not?
Physicists should not be in charge of naming things.
So we just call the magnetic moment G. And the magnetic moment of these particles is essentially, it's the particle's response to a magnetic field. Like, if you shove an electron through a magnetic field, how does that electron feel about the magnetic field around it? How strongly does it interact with it? Same for the muon. How strongly does it interact?
And so when I build my muon computer, I'll need to build proper bracing on my wires to handle how the muon's going to handle being jammed around the different circuitry of my muon computer.
Exactly. And that's what this latest experiment is it's a giant muon blaster that's shooting out a bunch of muons, and then they put it in a giant ring and watch how they behave under these strong magnetic fields.
And G is it doing what it's supposed to. You just go like
it's not, and so that
no, but just in general, like that's why it's the G. I guess that's like I know what's been detected is different from what it was expected, but G is the number they put to it.
Right. So that's what we're trying to measure. What is the G of the muon?
Right.
Now, you can calculate this number theoretically, and then you can measure this number experimentally. And so that's what you want these things to match up. You want the theoretical prediction to match up with the experimental observation.
Right.
When you do a very simple, naive, unsophisticated prediction of what G should be, you get the number 2 in whatever units. I forget what the units are. It's probably dimensionless. It's just 2. When you do a more sophisticated analysis and you really dig in, you see it's like 2 and a little bit. So what we're really interested in is measuring that little bit, which is G minus 2.
Right. And that's why it's G minus 2.
That's why it's called G minus 2, because we're interested in measuring that tiny, tiny, tiny little difference away from 2.
Yeah. And it's funny, you like knowing whether or not it's G, is it G2 or is it G minus 2? And it, you know, that's what really separates us, is if we know how to properly say G minus 2.
That's the shibboleth.
Yeah, that's it. Exactly. That's how you can tell people are in the know. That's the secret passcode. Is you're like G minus 2. All right. So physicists are trying to detect this little bit, this remainder, and but the theorists had predicted a number for this, right?
Yes,
they predicted the remainder. The remainder is not a surprise.
Right, exactly. We knew it was a little bit away from 2. We've already done this experiment for the electron, and the theoretical calculations and the experimental observations all matched up. It was like 2 plus a little bit, and everyone was happy.
Right.
But then we said, well, let's do it on the muon because, hey, this should work. And now it's looking like it might not work.
And so I guess with the electron, standard model lived up to the theory,
to the hype.
Everything's fine, but because the muon is so much more massive, sort of smashes its way around the particle accelerator. It's easier to notice additional shifts from what you're predicting from the theory.
Yeah. The difference away from 2 is a little bit stronger. Your experimental setup, you're exactly right. Because the muon is heavier, there are more interactions. And so this gives you a different window into the world of the standard model.
And so what did the experimenters, really the heroes of the story, find?
So the latest experiment, which was done at Fermilab, there was an older experiment from 15 years ago over at Brookhaven where they ran this giant experiment for like 2 years, collected a mountain of data because you're looking for very, very tiny little things. They collected this mountain of data, found a difference between what they were measuring and what the standard model had predicted. Everyone's like, wow, this is weird. I wish we had more money, and we don't. So we'd like to replicate it. We'd like to build a whole new apparatus, but that's kind of expensive. So let's take the entire magnetic confinement ring, our muon box, and move it over to Fermilab, and Fermilab can pump even more muons into it, and we can measure this again. And so the new measurement over at Fermilab confirms the one from 15 years ago. And so here we have now 15 years, 2 somewhat independent experiments. It's not a completely perfect replication, but it's pretty close, where an experimental result is disagreeing with the prediction from the standard model.
And has this happened before?
Yes and no.
Or to this level of precision, to this many sigmas?
To this level of precision, no. Like you run an experiment and there's some weird anomaly. There's something you don't understand. There's some disagreement, but then you keep running it and then it just kind of swings back and it all goes away. And that's why this result, this G-2 measurement is so interesting, is because the standard model has held up for like 6-7 decades. And it's been experimentally verified over and over and over and over again. In fact, the electron G-2 measurement, I've read that it's the most accurate or most precise measurement ever performed in human history.
Yeah.
And so yay. But we also know the standard model is incomplete. We know it's not done. We know it does not perfectly explain the whole entire universe.
How do we know that? It seems done. They found the Higgs boson. Every piece. I mean, sure, it's a horrible mess, but
it's a nasty mess.
Yeah,
but
nature can be
incomplete.
A mess. How do we know that it's incomplete?
Yeah, we know it's incomplete because of the mass of the neutrino. is not predicted by the standard model. Dark matter, whatever the heck dark matter is not one of the standard model particles.
And yet it's most things.
We do not have a quantum theory of gravity. So like there are, we do not have theories of like supersymmetry. Like there are a list of things that the standard model can't do.
Right. And so we know that it's incomplete, and yet it just refuses to have any chip in its armor.
Exactly. So we know it's incomplete, but we don't know what is complete, and we don't have any experimental leverage to propel us to something that could be complete. So if this G-2 experiment holds up, right, and there really is no way for the standard model to explain this result, which is still ambiguous. I want to get into the theory a little bit and how it's not as airtight. But if we can't explain the result, then now we need to come up with a way to explain that result, which will by definition be an extension of the standard model and maybe propel us to some new understanding of physics.
So how good is this result? How accurate?
I don't know the accuracy off the top of my head.
Sigma, sorry. I was gonna.
Okay. Yeah. So I didn't know the decimal places, but yeah, the disagreement between theory and experiment is 4.2 standard deviations, right, which is pretty high. There's some arbitrary standards out there like 5 sigma. Well, what does to claim a detection?
What does 4.2 mean? So, like, if I say like when I say, oh, this has 4.2 standard deviations, if I'm going to tell someone that that's a good result or a bad result, in sort of statistical terms, what am I saying?
It's something, I don't know the precise number off the top of my head, but it's something like getting this result by pure random chance. You only have like a 1 in, I don't know, like 100,000.
Right. Okay.
Probability of getting this result from purely random chance.
Right. Okay. So it would be as if you won the lottery to get this result.
And yeah. It's like that's supremely unlucky. And so we tend to think the difference is not because of random chance, but because there's an actual real difference.
Right. Okay. All right. Okay. So then I'd like to get into then what this means. What does I mean, if this measurement is different from what the theory is suggesting, what are the implications for the standard model?
Yeah, there are 3 possible implications. One is there's something wrong with the experiment that we don't fully understand. And because they reused a lot of the gear from the original Brookhaven experiment, that's still a possibility. This wasn't a pure replication.
Right. So that would be like the neutrino going faster than the speed of light.
Yeah, that was just a cable that wasn't plugged in all the way.
The point being, but you could take that bad cable to the new instrument, and plug it in.
Exactly, and you're like, oh, if the grad student doesn't plug in the cable the same way again, you're going to get the same result. So if there's some gnome inside of the magnetic confinement chamber that's like poking at the muons, you haven't gotten rid of that gnome.
Yes,
I hate gnomes.
That seems
in particle physics.
I gotta say, that seems super likely to me. I mean, I'm sure they've tried to remove
my personal mantra, if it's interesting, is probably wrong.
Yeah.
The most boring explanation is that there's something off about the experiment itself.
Yeah. Yes.
But okay, the experiment is the experiment. If we really do understand the uncertainties, the statistics, the systematics to the level we say we do, then we have to go with it and we have to explore other options. So, okay. Even though that's the most boring explanation, let's talk about the others.
Okay. But I'm going to ask you to place your bets at the end. But yeah, please, let's continue.
Okay, fair.
Yeah.
The next place you can go is that the standard model predictions for this value for G-2 are exceedingly difficult to make. This is not just like, let's work out the math on our chalkboards. This is a complicated bootstrap process where you make one measurement of something else related to muons, plug that into a calculation, run a simulation, do a bunch of analysis, do another experiment to fill in another gap, and then get yourself up to this theoretical prediction. there are a lot of things that can go wrong in that calculation. There are a lot of things that we don't fully understand. There are a lot of things that we have to approximate in order to get that that estimate for
Right.
G minus 2. And so there might be little things going wrong, especially if no one has really worked on this problem in 15 or 20 years, where the Brookhaven result came out and you're like, oh, that's weird. Well, let's keep working on something else while those Brookhaven fellas and
Right.
ladies figure out what's going wrong. And then 15 years later, it's now verified by Fermilab, and you're like, oh, whoops, we actually haven't updated any of our
Right.
calculations from 15, 20 years ago.
And so like literally somebody forgot to carry the 2 while they were doing the math that predicts the outcome.
Yes.
Right.
That's perfectly possible, especially the muon's interaction with the strong force, which influences this G minus 2 answer, is very complicated, not well understood. And
Right.
there are possibilities there for miscalculations, misunderstanding, leaving out something that turns out to be important. Like the electron G minus 2 calculation involves something like 10,000 Feynman diagrams.
Right. Yeah. And so you can imagine that at some point someone made the prediction that peer review, somebody didn't catch the mistake in the math. There hasn't been a lot of emphasis placed on looking over these papers with a fine-tooth comb. And here we are with a final number. That's just like the prediction number is wrong. And if people go back through
and it doesn't even
the
have
papers,
exactly. Yeah, it doesn't even have to be a mistake. It could just be we made a reasonable set of approximations to get to this result, and it turns out those reasonable approximations aren't good enough. We don't need 10,000 Feynman diagrams. We need 10,001 Feynman diagrams.
Yes. So okay. So a problem with the machine, a mistake in the calculation of the prediction. Those are boring.
Those are boring.
Yeah. So so now get to the good stuff.
The good stuff is new physics. What new physics? We have no idea.
Well, okay. Somebody's got to have an idea. Nobody, like, what does it mean?
Well, here's the thing. We have no consistent working theory of physics beyond the standard model.
Right.
The standard model calculations themselves took years of people and like intense resources just to get the G minus 2 prediction. If you have your own idea of what is causing this anomalous result, it's going to take a fully consistent theory and years of resources and dedication, hard work in order to match that prediction or match the observation.
But there is a dam filled with theories, papers that have been published, theorists that have been working to try to extend the standard model in every conceivable way you can imagine. Does this help alleviate the logjam and give people a direction to go forward?
Absolutely. And this is why people get so excited by something like G minus 2, because you can sit here as a theorist spinning your wheels for decades, like coming up with cool ideas and new interactions and new forces and new couplings and on and on and on and on. But as long as the standard model holds up to experiment, you can't do anything with it. But now there's something potentially that breaks the standard model in a very obvious, community agreed upon way. And so now your goal is to take your favorite pet theory that you wrote up in 1997 and see if you can use it to explain the discrepancy in G minus 2.
And what do we do with that next then? I mean, if you, so like you wrote a paper and you're like, why won't anybody listen to me? Why do they keep putting me in an insane asylum? The G minus 2 experiment is not going to find what they're expecting because I'm predicting the mu Reno, whatever.
Yeah. any of these new theories,
Yeah.
or old theories that have yet to be realized,
Yeah.
if they can explain the G-2 discrepancy, there's going to be other things about them. There might be some new particles floating around in the universe, some new forces, some new interactions. And then because that theory is now able to explain the G-2, we can take it a lot more seriously. We can focus on a little bit more. We can work a little bit harder, and then look for other predictions and confirm it. And then if the theory continues to succeed and make new predictions and agree with the experiment, then we can update our view of physics.
So for example, I've decided that the muon has a subparticle called the murino that is like a fraction of the mass of the muon, and is sort of pops out of it every fraction of a second and then is reabsorbed by it. And together, the two of them cause a bigger magnetic moment than just the muon alone.
There you go.
Did it?
Yeah, you can do that. And then
here's the math.
Yeah, exactly. There's going to be a lot of math to go along with that. And we use the math to make other predictions about how the universe should behave at these energies and scales. And we can go out and test that. And then, yay, we've discovered a new particle or a new force. And, physics marches on.
So then what comes next? Do you figure somebody is going to, how do we know which of those is the case?
I think what comes next is a deluge of theoretical papers describing the G-2 result.
I already came up with mine, so I should just throw it in the mix.
Yep. Yeah, exactly. It's going to flood the archive. It will provide headlines for you for at least a year. So that's nice.
Yeah.
So there's going to be tons of theoretical papers. There's going to be more analysis from the Fermilab team. This was only their first batch of data. They are continuing their analysis. They have more data to crunch through. They will provide an update in 6 months or a year. The difference might go away. It might get stronger. It might stay the same. Meanwhile, physicists are also going to really poke at these results. We're going to really dig into the experiment, the systematic uncertainty. Do we really understand this experiment the way we think we understand this experiment? Is it really operating when we tell it to go? Is it really going? When we tell it to stop, is it really stopping? So there's going to be a lot of poking and prodding at that Fermilab experimental setup. This might drive some funding over the next few years to do a G-2 Patois experiment, maybe with a new magnetic box for the muons to hang out in. Because if this is legit and it's interesting, it's worth investing in, and we should see if we can truly replicate this. There might be an experiment in Europe or China or India that have the capabilities to try to replicate this on their own. So it's what comes next is just more science.
But right now, particle physicists are at this fork in the road where they're trying to figure out what to do beyond the Large Hadron Collider. I don't know if you could adapt this experiment into the LHC, or you need a very specific setup like the one they have at Brookhaven. But they're talking about essentially just building a bigger particle accelerator and then just smashing particles together and just looking through the rubble to just find anything, which is not a super productive way to move forward from this point on. Does this sort of show up at the right moment to go, let's try this instead?
Yeah, I think it does actually. The LHC was designed, you're right, to smash things together and look through the rubble, but it was designed with two things in mind.
To find the Higgs boson.
Yeah, find the Higgs boson, and also to find evidence for supersymmetry, which was our theorists' best guess as to what came after the Standard Model. Higgs boson, yay, Nobel Prizes everywhere. Supersymmetry, nada. There was zero evidence for supersymmetry at the Large Hadron Collider. So big particle collider experiments like this, do have an uncertain future because they're not doing the thing that we built them to do.
Mm-hmm.
And so now there is more of a case for smaller, more dedicated, instead of general purpose colliders. Well, let's build something that just spits out muons. Let's look for more neutrinos. Let's go hyper focused, because that's where the interesting edges of the standard model might be now.
And then scale up any of those experiments that seem to be delivering the results.
Yeah, scale them up, run them longer, run 2 of them that are built by different teams. Before we jump into the standard model of particle physics is broken bandwagon, we got to be really sure about it.
Right. And so, I mean, as I mentioned, with the... Do you know, and maybe this is going to sort of be outside your purview, do you know if this result in any way relates to any predictions for supersymmetry? I'm sure the supersymmetrists will be jumping all over it.
It's going to be very, very hard because large swaths of supersymmetry have already been ruled out. Supersymmetry is more of a class of ideas rather than a specific concept. But the vast majority of supersymmetry models have already been ruled out. So if you want your supersymmetry model, the one you wrote up in 1997, if you wanted to explain the muon G-2 result, you also have to confront the fact that it didn't show up at the LHC. And it's totally possible to do it, but you're going to have to do some real stretching and distorting in order to get that to work.
Yeah, cool. I want to give the audience a chance to answer questions, and I think we'll let you go.
All right, let's do it.
So Arjun asks, does the muon make, what makes the muon better than the electron? Would the tau offer any advantages? You actually did table the tau, so maybe we can bring it back onto the table.
The muon has a few advantages, like we mentioned. It's heavier. The interactions with the strong force are a little bit more opaque and harder to understand. So this is a good place to push on the standard model. The tau is even heavier, so it has an even shorter lifetime. It's even harder to produce. And so you don't get the volume of data that you get from a muon experiment. So muon is like this good middle ground between I can push on the boundary of physics and I can get a lot of data.
Right. And so the tau, but I'm guessing, like, if you could tame the tau, it would show an even more forceful moment as it's grinding around your machine.
Yeah, it's G-2 measurement. Yeah, exactly. Like if you could produce a bajillion taus, it has its own interactions with the forces of nature.
Yeah.
And so potentially larger discrepancy. As far as I'm aware, we haven't dug as deep into the G-2 calculation of the tau as we have for the muon and the electron.
Right. Awesome. All right. Well, Paul, thanks so much for taking the time to chat with us today. What are you working on that people should come and enjoy?
Hey, you should check out Discovery Channel and Discovery Plus streaming service. I'm part of a wonderful show called How the Universe Works, which premiered 3 weeks ago, and new episodes are dropping every week. It's a real fun adventure through the cosmos. My book is still available for sale, How to Die in Space. Big news, we have, it's going to get translated into Chinese, Russian, and Polish, and hopefully more to come. So that's going to be fun. I can't wait to see what those covers look like. And just doing the fun podcast, YouTube, writing thing.
Fantastic. Well, stay safe. Get your next vaccine on time. And I look forward to being able to hang out again in person at some point in the future.
That sounds like fun.
All right, man. Take care. Thanks a lot.
Take it easy.
Now I got to find the button. There it is.